Okay, well, hopefully in your last class, you were able to take a look at this problem and just by just trying different combinations, come up with the combination of Roma and cherry tomato plants that gave you the most pounds of tomatoes. And if you haven't, give that a try right now, just by kind of plugging and trying just different things. See if you can calculate the maximum number of pounds that you can come up with of tomatoes. That's going to be important as we go into the rest of our notes. All right, so what we're going to learn today is called linear programming. And linear programming was first used in World War II when they had to determine the most efficient way to get the most food to the troops on the train systems that they had available. And there was so many different variables involved, they had to come up with a method to try and maximize, the most food they could get with the least amount of money and the least amount of travel. All right, so this is called linear programming, which is a method used to determine how to achieve the best results when given several sets of restrictions. For example, you might want to maximize your profit or any output possible, or you might want to get the minimum cost or time that's possible. So in it, some of the vocabulary will be a constraint is an inequality that places a limit on the possible answers to a problem. So it's like the whole world is not your possibility. There's going to be certain restrictions. For example, there may be a limit to how much money can be spent or how much time is available. So next we have an objective function is another term that you need to know. It is an equation that can be used to calculate the quantity that you're trying to maximize or minimize. That should be R, minimize. In the introductory problem that we looked at, we were trying to maximize the number of pounds of tomatoes. For that one, the objective function would be, okay, so we need to look back to calculate how many tomatoes we wanted. We had to look on our table here where it said that Roma's got 8 pounds per plant and the cherries were 10 pounds per plant. So that's how we calculated how many pounds we'd get. So the number of pounds would be, let's see, 8, we'll let Roma be X and cherry be Y. So we'd have 8 times every Roma plant plus 10 times every cherry plant. And that would be our objective function. We want to make that as big as we possibly can. But we can't go up into the hundreds and 200s because we've got some constraints. So inequalities that are going to keep us from just making tons and tons of tomato plants or buying and producing. All right, so let's look now at the inequalities that we might need to come up with over here. So when we take a look at, again, at our information here, we can have at most 15 plants. So that's the biggest number that we can have. So since X represents the number of Roma and Y represents the number of cherries, we'd have to say that X plus Y has got to be less than or equal to 15. So I'm going to write those down. So X plus Y has got to be less than or equal to 15. So the number of plants has to be less than or equal to 15. Then the other thing that we need to do, we need to talk in terms of money. And maybe I can do this in a different color. So here you can see the money here. At most we have $40 to spend. So then we've got to kind of take into account the cost of each one of them. So each of the Roma plants, which is X, costs $2 each. So we'd have to say that 2 times X tells me how much money I'm going to spend on Roma plants. And see, cherry plants are $3 each, and they were represented by Y, so 3Y is going to be how much we'd spend on cherry plants, and it can be no more than $40. So again, less than or equal to 40 for that. So we have another equation, which we're going to write over here. 2X plus 3Y is going to be less than or equal to 40. All right, so what I've done here is I've graphed those two equations for you. And truthfully, the best way to do these constraints typically would be to do intercepts. So if x is 0, y is 15, which is this one right there. And if y was 0, x is 15, which was this one here. And then you can see that those are connected right there. Then for the other one, if x is 0, ooh, that's not going to come out very nice, is it? Y is going to be 40. So that's not going to be exact on that. So that's going to be 40 thirds. So it's going to be what? 13 1/3, which is this one right here. So maybe not the absolute best to do that. And then, but if y was 0, x is 20, which is going off the screen over here. All right, but these two, these are going to be my intersections. And since you've got to be careful when you decide which way to shade, since we're not solving it for y, but if I substitute the 0, 0 in, 0 plus 0, 0 is less than 15 is true, I'm going to find that I'm going to shade underneath my green line and get something that looks like this. Then I'll do the same thing and try these. If I put 0, 0 in again, it's also less than 40, so I'm going to shade. The solutions are going to be underneath the other line. So where they overlap would be this section here that I have highlighted in the darker area. This is called the feasible region, which is the solution to the system of inequalities. And it's the section of the graph where all the inequalities overlap. So if we had more than two, where all of them do. The corner points that we were talking about are the corner points of the feasible region written as ordered pairs, which I will do on the next video.